took it to a spa. Shoes? Massage?
Sure, all those things would be nice. I hope you get that.
Be serious now, people. You're on film. So let's see. We were talking about crystallographic root systems, right? We talked about how they were characterized by their Cartan matrices. Right? We remember that we just make a matrix where the entry alpha beta is the product of alpha and beta check. And so now what? Well, we know that each crystallographic root system gives you a Coxeter group. And Coxeter groups are characterized by their Dynkin diagrams. Sorry, the Coxeter diagram. We talked about how this is also equivalent to the Dynkin diagram. And Coxeter groups are characterized by their Coxeter matrix, or equivalently by their Coxeter diagram, right? So, but this only goes in this direction because we saw already that not every Coxeter group arises from a crystallographic root system, okay? But we did see, for example, how to go from the root system to the Coxeter group. We saw how to get from the Dynkin diagram to the Coxeter diagram, from the Cartan matrix to the Coxeter matrix. We basically know how to go this way. And let me just remind you how that goes. It's very simple. So the way you translate from here to here is basically by this table that allows you to read from the Cartan matrix the Coxeter matrix. And it goes like this. We said that these numbers can be 0, 1, 2, 3, or greater than or equal to 4. And accordingly, the MIJs are going to take the values 2, 3, 4, 6, and infinity. Okay? Now, last time we talked about how all of these numbers can be realized. Okay? And then the main theorem that I proved last time was basically telling us exactly which integer matrices are Cartan matrices. So let me remind you, maybe I'll write it over here. The theorem that I proved last time is this: an integer square matrix is the Cartan matrix of a crystallographic root system if and only if we have the following conditions. First of all, the diagonal should consist of 2's. Off the diagonal, you should have non-negative integers, sorry, non-positive integers. The zeros are located symmetrically. And then we have this condition on cycles. So if you have a cycle in your Dynkin diagram, then you need this product condition that A I1 I2 divided by A I2 I1 times, etc., up until A I N I1 divided by A I1 IN should be equal to 1. Okay. And so this really tells the full story of classifying integer Cartan matrices, or equivalently classifying crystallographic root systems. We understand what a crystallographic root system is. Okay. So now what I would like to do is figure out this part of the story. Okay. We understand this part. We have classified these guys. Now, today I want to understand what are the Coxeter groups that come from crystallographic root systems. Okay. And so my goal for today is to prove a theorem that sounds very similar to this, and basically should read something like a Coxeter system W comma S is the reflection group, or the Coxeter group, of a crystallographic root system if and only if something. Okay. So the goal today is to fill in the blank and understand exactly what are the Coxeter systems that come from crystallographic things. Okay. Now, from that table, we can already infer one necessary condition, which is that the exponents, sorry, the MIJs have to be in this list, right? But as you can imagine, just like here these three conditions were not enough, here this condition is not enough, and we're going to need a condition that looks kind of like this cycle condition. So that's what we will do. Okay, and let me tell you what that condition is. So what that condition is that in each cycle of the Coxeter diagram containing no infinities, there must be an even number of 4s and an even number of 6s. And that's it. It's an if and only if. Okay. So, of course, part of the point is to understand what this condition has to do with this condition. But if you look at this, this gives you, the nicest result possible as to, if I give you a Coxeter diagram and I ask you, is this coming from a crystallographic root system, then it's really, really easy. All you have to do is look at the cycles, and if a cycle doesn't have an infinity, you just count the number of 4s, count the number of 6s. And if those numbers are even for every cycle, then it comes from a crystallographic root system, and otherwise it doesn't. Okay. And so my goal for today is to prove this. Okay. So let me just erase all this stuff. And maybe the only thing that I would like to do is keep this little table, which we're going to keep referring to. Okay. Uh-huh. So So it says that in each cycle of the Coxeter diagram containing no infinities, there is an even number of 4s and an even number of 6s. So it's two conditions. And somehow that means that you don't care about the 3s or the 2s. We'll see why.
But if there's an infinity in that cycle, then we don't care.
And if there is an infinity in that cycle, then there's nothing to check. Okay. So let's see. Let's talk about necessity. Why is this cycle condition necessary? Let's consider some cycle like this, and let's suppose that it's infinity free. Okay. So that means that there's 2s, 3s, 4s, and 6s. Is that right? Well, that's actually not exactly right, because if you remember, you never draw the 2s in a Coxeter diagram. So that means that 2s don't appear as edges. And so that means that these are all 3s, 4s, and 6s. Okay? And so, I don't know, let's just pick some random numbers. 3. Let me just make these different colors. So 3s, 4s, and 6s. Okay, so there's a cycle. Now, if you see the cycle, you see that there's an odd number of 6s, and so somehow it must be impossible to get this. This cannot come from a crystallographic root system. Okay. Well, what's the point? The point is that whenever you see let's translate from the Dinkin diagram to the Coxeter diagram. So what you see in the Coxeter diagram looks like this, like this, like this, like this, or like this. This is Coxeter. In the Dinkin diagram, what you're going to see is this is a double edge, right, pointing in some direction. This is a triple edge pointing in some direction. And this is something like A, B. So the thing is, this is Aij, this is Aji, and remember that the thing about this is that if we have an edge like this one, this is a 2 and a 1. If you have an edge like this one, then the length of this root divided by the length of this root has to be square root of 2. In other words, this, did I write it like this? Well, anyway, alpha I comma alpha I divided by alpha j comma alpha j in this case is square root of 2. In this case, it's square root of 3. In this case, it's 1. And in this case, it's something like square root of a over square root of b. And in this case, we have no information. Okay. But so then, what do we get? You see, let's say this is alpha 1, okay, and this is alpha 2. So what we get is that alpha 1 divided by alpha 2 is either square root of 3 or 1 over square root of 3, according to whether this thing is pointing one direction or the other direction. Right? Sorry, the 3s are these guys which correspond to 1s. So this should be a 1. Okay. Now, if I do alpha 2 divided by alpha 3, then I see a 4, so that means that these guys are related by square root of 2 or 1 over square root of 2. Okay. Then for alpha 3 and alpha 4, we get that this is equal to it's a 6, so it's either square root of 3 or 1 over square root of 3, etc. Okay? And so I go around the circle and I do this for each edge. Now, what do I get when I multiply all of this? Well, what I get is alpha 1 divided by alpha 2 times alpha 2 divided by alpha 3, etc. We know we're going to get 1. Okay? And on the right-hand side, what are we going to get? Well, we only see 3s, 4s, and 6s, which means that on the right-hand side, we're going to see 1s, square root of 2s, and square root of 3s, maybe to a positive or to a negative power. So what we're going to get is square root of 2 raised to some power times square root of 3 raised to some power. Okay. But we know that square root of 2 and square root of 3 are irrational, and they're also independent from each other. So when you have something like this, actually, it must be the case, because a and b are integers, it must be the case that both a and b are 0. It's the only way that you could have square root of 2 to some integer times square root of 3 to some integer equal to 1. Okay? A equals b equals 0. So, for example, a equals 0. Okay? So that means that the total power of square root of 2 that you see over here is 0. And that means that the number of times you chose square root of 2 is equal to the number of times you chose 1 over square root of 2. And that means that you have an even number. Okay? So this means even number of square root of 2's and 1 over square root of 2's counted together, an even number of square root of 3's and 1 over square root of 3's counted together. And that means that you must have an even number of edges labeled 4 and an even number of edges labeled 6. And now you see the reason that we don't care about the 3's, because these edges labeled 3 give me 1's here, and so they're not noticed in this procedure. Okay? So that proves to me necessity. Okay. Any questions about necessity? Okay. So let's talk about sufficiency then. So for sufficiency now, what I have to do is I'm given some graph that has this condition, okay, and I have to show that that graph really comes from a crystallographic root system. Okay? So let's say that we're given this graph, and maybe what I want to do is do just a big example of this. I think if we do it for a big example, then you'll see how to do this. So let's consider, I'm going to just draw some big graph. So maybe I'll start with this. And let me just kind of add some things to it. So there's some graph, and now I'm going to try to label this so that every infinity free cycle has an even number of 4's and 6's. So if I make a mistake, please let me know. And let's put some infinities also, just to see how to deal with those. So maybe that's an infinity. And so, I don't know, let's say, what's bad? This cycle is fine. This cycle needs another 4, so let's put a 4 here. This cycle needs another 4 and another 6. So I'm kind of in trouble. So let me then, I don't know, just add like something like this, and add an edge here, and 4, 6, and now Let me fix that problem with an infinity over here. Well, no, this is too messy. Let's do something nice like this. There you go. And maybe here we have 4, 4, 4, 4. And maybe here we have some 6, 6, 6, 6, and let me call this a 3. Does that look good? Maybe we'll put a 4 here and an infinity here and a 4 here. How's that? Does that work?
You got those two unlabeled edges.
Unlabeled are 3s, so 3. Actually, let me keep them unlabeled so that I can make my picture a little cleaner. So if it's unlabeled, then it's a 3. So I think that works.
If you do this for some spanning set of cycles, it'll work on the whole thing.
Yeah, so we'll get to that.
Because there are obviously some big cycles in there.
Because yeah, for example, so actually let's address that point right away. So how many cycles does this graph have? Well, maybe that's a harder question than you might realize at first, because okay, well, here's 6 easy cycles, or 7. Can I count? 7. 1, 2, 3, 4, 5, 6, 7. But there's other cycles, like maybe you can go around this way and then this way and then back here, yeah. Or maybe I can go around the whole thing. Okay. And so, do I really want to check all of these possible cycles? Well, here's maybe a lemma that allows me to not have to do that. Lemma says that if I check it for these 7 cycles, then I've effectively checked it for all the cycles. So let's say that if what's the good way to say this? If the evenness condition holds for a spanning set of cycles, then it holds for all cycles. What's a spanning set of cycles?
Cycles that spans the graph for every edge.
It's so basically every other cycle should be able to be seen as a combination of these 2 cycles. So for example, I mean, let me just give you a sketch. Anyway, I mean, this is not really part of my proof. This is just kind of a shortcut to be able to check my example more easily. So let me not give you a complete proof, rigorous definition of what I mean by this. But the point is this. The point is that if you checked it for a cycle that looks like this, and you checked it for a cycle that looks like this, then you want to deduce that you checked it for the big one also. Okay. So why is that? For example, let's say that these cycles are both infinity free. So for example, this one has an even number of 4s, and this one has an even number of 4s. Okay. So how do I check that now this one has an even number of 4s? Well, basically the thing is that, I mean, you kind of figure out what happens here, but the parity of the number of 4s in this piece should be equal to the parity of the number of 4s in this piece, if they add up to an even number. So the number of 4s here and the number of 4s here have the same parity. By the same reason, the number of 4s here and the number of 4s here have the same parity, and that means that the number of 4s here and the number of 4s here have the same parity, which means that the parity condition holds for the big cycle. Okay. And so, again, this is just kind of a convenient thing so that we can believe that this example is good, because now we just check these 7 cycles, and do they work?
Problem, the left one. You take the left one and then the upper left one next to it, you get 3 4s.
Oh, because this is a bad cycle. So I have to fix it by putting a 4 here, let's say. And now it's good. Okay, so somehow I'm supposed to make a crystallographic root system out of this information. Okay. Well, now that sounds like a much more complicated task than if we think about it from this correspondence. Okay. Because now I know that exactly what the Dinkin diagrams look like. And so instead of building a crystallographic root system, let me build a Dinkin diagram, where the Dinkin diagram is just going to be basically the same thing as this, where the only thing I have to do is translate this into this. Okay. Do I? Oh, this is a problem, this cycle, so let me do what?
That one. But if the one you just added, if you move it up, no. Yeah.
Okay.
You see, we're proving a point that maybe these things are kind of rare. It's not so easy to satisfy this condition, but now I satisfy it, I think. You know, let me just do it. So here I have 4 4s, 4 6s. Here I have 2 4s, no 6s. Here I have 2 4s, 4 6s. 4 4s, 2 4s, and then infinity, so that's fine. Okay. Good. So what do I have to do now? Well, I have to basically take this Coxeter diagram and make it into a Dinkin diagram. Okay. So what I have to do basically is now take these 4s and make them into double edges, take these 6s and make them into triple edges, and orient them in the correct way, and then do something to the infinities. Okay. But if I don't see an edge, then I still don't have an edge here, and if I see an unlabeled edge here, I leave it unlabeled. So I have to figure out what to do with the 4s, what to do with the 6s, what to do with the infinities. Okay. So what should I do? Well, again, so if I take a 4, I have to make it into a double edge, which I have to orient in some way. If I take a 6, I have to make it into a triple edge and orient it in some way. And if I take an infinity, if I see an infinity, then I have a lot of freedom. All I have to do is choose A and B, which multiply to something greater than or equal to 4. Okay. Well, that sounds easy, but of course there's some additional conditions, right? Because I don't want to do this in any old random way. I want to do it in a way that is consistent with my theorem. So let's see what I have to be careful about in this theorem. I have to satisfy these conditions. So this one is going to be satisfied for free because there's no loops in my graph from I to I. These three are satisfied for free, basically. The only thing that I have to check is this condition that around the cycles, product is equal to 1. Okay. So I need to pick my arrows in a way that the product is equal to 1. Now, again, the point is that if I introduce an arrow like this, then if this is A, I1, I2, and this is A, I2, I1, I get that A, I1, I2 divided by A, I2, I1 should be square root of 2. And if I direct it in the other direction, it's 1 over square root of 2. Okay? So what do I have to do in this cycle, for example? I have to orient the 4s and the 6s. Let's focus on the 4s. So I have to orient 4 arrows. Okay? And I have to orient them in such a way that when I travel around the circle, these square root of 2s that appear multiply to 1. In other words, what I need to do is choose 2 guys to be square root of 2 and 2 guys to be 1 over square root of 2. Okay? So what I need is, in each cycle, let me say in each infinity free cycle, I need that the number of double edges going one way should be equal to the number of double edges going in the other way. Right? When I travel around. That means when I travel around, I'm going to see the same number of square root of 2s, and 1 over square root of 2s, they're going to multiply to 1. I need to do this for the 6s also. So I need that the number of triple edges that I see in one direction is equal to the number of triple edges that I see in the other direction. So this for the infinity free cycles, and then once we've done that, let's figure out what to do with this cycle and this cycle. But for now, let's just make sure that we know how to do this part. Okay. Okay. Well, the nice thing about this is that, so let me say, then deal with infinity cycles. That's the plan. Okay. So the nice thing about this is that I subdivided it into smaller problems because this thing that I need to accomplish here only depends on the force and on nothing else. Okay. So what I'm going to do now is I'm going to take this graph and I'm going to do something fancy to it, which is that I'm going to just keep track of the force and eliminate everything else. Okay. So what is it that I'm going to do? Well, what I'm going to do is take this graph. If I see an edge labeled by a 4, I leave it alone. But if I see an edge that is not labeled by a 4, then I'm just going to contract it. I'm going to take this edge and just identify the two vertices. That means, for example, that all of these guys, so I'm going to contract everything but the 4s. Okay? So that means, for example, that these 6s are just going to become, like, this is glued to this is glued to this. All of these vertices are glued to each other, and so this cycle closes over here. What's the point? The point is that I want to walk around this cycle and count the number of 4s, and for that count, it's irrelevant if I see 6s here or not. So let me just forget about them. Okay? So again, I want to do this, and I want your help so that I don't make any mistakes, because this is kind of hard to do live. So let's start with maybe this part, okay? So let me draw this part here. I see 4, 4, 4, and then 4, and then these two guys got identified. Okay. Now, here's a 4 that goes out to here, but it's not really going out to here anymore because this got collapsed. So this now becomes this. This also got collapsed. Okay. This got collapsed, this got collapsed, this got collapsed, and so now this 4 and this 4 are going to look like this. Okay. This cycle disappeared. Now here, I have this cycle where this guy got identified with this one, this guy got identified, and so these two are identified, and they're coming out of this vertex, so now they're going to look like this. Here, I have this cycle. Now I only get these two 4s, where they're going to look like this. And then finally, this cycle, I already drew these two, and now I need to draw these other two, so I get something like this. Okay. Is it clear what I did there? Any questions about it? You have to kind of do it carefully, right? But the point is that, for example, these three vertices got lumped together, and if you do it carefully and identify, you get this picture. Okay. So these are the 4s coming from here. And now what I have to do is orient this in some way. Okay. And let me do the same thing with the 6s. So I'll contract all but the 6s. So what am I going to get now? Well, here I get a cycle of length 4. Right. Joined with another cycle of length 4 here. And these two cycles don't share an edge. They just share this vertex. And everything else gets clumped together. And so if I want to orient the 4 and the 6s, I just have to make sure that I'm able to orient this thing and this thing. Now, in this case, you can just do it by hand. It's very easy. You just have to make sure to orient so that each cycle has the same number of arrows in the right direction and in the wrong direction. But how do I do this in general? Well, the thing is, you look at these guys, and what property do these graphs have? Well, by assumption, in this graph, every cycle had an even number of 4s. Okay? So now here I'm keeping only the 4s, and so this thing only has even cycles. Okay. And this thing also only has even cycles. And so the question is, how do I take some random graph that only has even cycles and orient it? Okay. Well, maybe you know about graphs with only even cycles. Here's a nice fact about graphs with only even cycles. So there's something called bipartite graph. So a graph is bipartite if you can bipartition it into two sets of vertices so that all the edges go from the left set of vertices to the right set of vertices. So if I can partition the vertices into, let's say, a white set and a white, let's say if I can color the vertices black and white so that all edges connect a black and a white vertex. So the picture you should have in your head is that you have black vertices here, then white vertices here, and the edges just go from the top to the bottom. So this is what a bipartite graph looks like. But the thing is that if I give you a graph, I might draw it in a different way. Okay? I'm not going to draw it for you like this, and if I ask you if it's bipartite, you really have to check and see, can I move things around so that I have a top set of vertices and a bottom set of vertices? Okay? That's a bipartite graph. Okay?
So this is equivalent to if and only if there are no odd cycles.
Right, so here's my nice combinatorial lemma, is that a graph is bipartite if and only if it only has even cycles. All cycles have even length. Okay. So it's a nice simple lemma from graph theory. How do you prove something like this? Well, one direction is very easy. If I give you a bipartite graph, then that means you can draw it like this. And what does a cycle look like? Let's say you start at the top, you go to the bottom, you go to the top, you go to the bottom, you go to the top, you go to the bottom. If you get back to where you started, that means you're at the top. And so the number of steps you took is even, because it takes one step to get down and another one to get up. Okay, so that it's clear that if you have a cycle, it must have even length. Okay. Now, if I have a graph where all cycles have even length, I have to prove that it's bipartite. So what I have to do is color it. Okay. So let me show you how you do this. Let's do proof by example. And since we have a nice example here already, let's do it here. Here I have a graph with only even cycles. Okay. So I want to color it black and white. I want to color the vertices black and white. So what I'm going to do is say, just start randomly and say this is black. Well, that forces the neighbors of this guy to be white. So white. Then let me keep walking from white to black, from black to white, from white to black, from black to white. So proof by example, just walk around. Just walk around, coloring black, white, black, white, etc. Now, how do I know that I'm not going to get contradictory instructions? Because it could be that I start with black, then I go to white, then black, then white, then black, and then maybe now I go to this one and I want to color it white. Well, that's not going to happen because I'm never going to connect this and this because that would form an odd cycle. Because all the cycles are even, that means that I'm never going to get contradictory instructions. And I can do this. If the graph happens to be disconnected, if it has two pieces, then just do one and then the other one. Okay. So again, easy lemma. Okay. The very nice thing about this lemma is that if I now ask you to orient the edges of this thing in one sentence, then what are you going to do? From black to white. 4 words, okay? So what I'm going to do is say, okay, only even cycles, that means this thing is bipartite, so let me color it bipartite, and then let me just orient it from black to white. Okay? Black to white, black to white, black to white, black to white. Why is that going to guarantee that in every cycle I have the same thing going forward and backward? Because every cycle goes black, white, and so that means you go forward, backward, forward, backward. Okay. And so if I keep doing this black to white, then I'm going to have a coloring satisfying this. Okay. So that's great. I do that here. Then here I do the same thing. Let's say this is black, white, 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 black. So I said black to white, so I go like this. Okay. And then I simply uncontract. I basically look for each edge in the previous picture and orient them in that way. So this is going to be a little tricky also, but for example, this cycle is like this. Should I do this? You get the point, right? Well, I might as well do this. Why not? It's fun. Like that. So I oriented the 4s according to this picture. Now let me orient the 6s according to this picture. So I go like this, like this, like this, and like this. And then here the same thing. Like this, like this, and like this. Okay. And I have accomplished this. Okay. I have accomplished my first goal, which tells me that in all of these cycles that have no infinities, I have absolutely no problem. The product of these ai1, i2 divided by ai2, i1 is 1 in all of these cycles. Okay. The trouble now is, what do I do with these infinity cycles? Okay. Everything else is fine, but I have to do something to guarantee that these 3 cycles are okay. So what do I do? Well, let's think about it. So, for example, let me just draw that part of the graph over here. It looks like this. So these are the cycles that I'm not sure about yet. Let me make it a little bit more complicated. This is too easy. Well, I mean, let's just do it. So I have to figure out, I have to make these cycles have product 1, right? So, for example, I go around this cycle, okay? So what do I get? Let's say I1, I2, I3, I4, I5. So AI1, I2 divided by AI2, I1 is going to be 1 over square root of 2. Right? Then the next one is 1. The next one is 1. The next one is square root of 2. And now I have to fix the last one. Okay. How do I fix it? Well, I have to choose the number that multiplied with these gives me 1. Okay. And I don't have a choice. It has to be a 1. Okay. And so somehow I have to make this thing have product 1. Does that worry you? It's supposed to be greater than 4. But, 1 is equal to 10 divided by 10. Or square root of 10 divided by square root of 10. And I just have to pick any two numbers, a and b, that multiply to something bigger than 4. I don't want to pick 1 and 1 because that won't do. But if I pick 10 and 10, I'm going to get still the correct ratio. Okay. So maybe I just decide, okay, well, let me just call this 10, 10. And I get square root of 10 divided by square root of 10. I'm done. And so you see the thing is that you have so much freedom here because you're kind of going around the cycle. Now you have to figure out what number to put here. And what you have is some rational number. Okay. But you're allowed to choose any a and b here. And so you can just make this value be the correct rational number. And this was a good example, actually, because you might have to do this if a, b is less than 4. Okay. So I fixed this one. What about this infinity? What do I need to do here? Well, here there might be another problem, which is that this infinity is being given two instructions. According to this, it should take one value, according to this cycle, and according to the cycle, it should take another value. So do they agree? Well, let's see. According to this cycle, what number do I need to put here? Well, again, this is 1 over square root of 2, and this is square root of 2. So again, I have product equal to 1. And so again, I have to choose numbers here whose product is equal to 1. So maybe I want to be interesting and not choose 10 again. 5 and 5, who knows? Okay. And then I have to pray that I got it right in this cycle, but it turns out that I did, right? Because here I have square root of 5 over square root of 5 times square root of 10 over square root of 10. And of course, it's not a matter of prayer. I mean, there's a reason to this, which is basically the same reason that I just erased here. Okay? The point is that if you have two cycles, I mean, when you're gonna, what do? I have to fill in an infinity. Okay. So if that infinity is the last unlabeled edge in a cycle, I have to be careful. But if that infinity is not the last edge in any cycle, then I just label it randomly, right? So if I have my graph like this, and I have an infinity here, and an infinity here, and an infinity here, then I can just give these two things random values, okay? And I just have to worry about this one, which, let me move it over here. Okay. What value do I give to this guy? Well, whatever this cycle tells me to give it, okay? The only problem I might have is that a different cycle wants to give it a different value. What's that situation like? It looks like this, okay? So it could be that according to this cycle, I want to give it one value, and according to this cycle, I want to give it another value. But why is that not going to happen? Because the product in this cycle is 1. And what that means is that this product is equal to 1 over this product. And so the number that I want to give to this one is 1 over the number that I want to give to this one backwards. And so the requirement from this cycle and from this cycle is the same, and I just make infinity take that value. Okay. So this is what I mean by dealing with cycles with infinities. Okay. So in this example, what we chose to do is this. We chose to put a 10 and a 10 here. We chose to put a 5 and a 5 here. And now we just regard this as a Dynkin diagram. This Dynkin diagram satisfies the conditions of the theorem that we proved last time. And that means that it corresponds to a crystallographic root system. And by this dictionary, we do get the correct Coxeter group.
So if this triangle cycle over here that was 4, 4, infinity, if there is an infinity in there, we can have as many 4s as we want, right? So say we had 3 4s there.
So say we had something like this. Yeah, because I mean, here it just worked out to be 1, but it could be something stranger, right? It could be maybe we had an infinity here, and maybe here we had a 4 and a 6 and a 4, like that. Okay.
But we can't really do a bipartite graph that part.
One thing I have to be careful actually is I have to get this cycle right, which I didn't. But this cycle has an infinity, so I don't care. But the thing is that like, you know, this 4 I can just orient it in any way that I want because it's not in any cycles, in any infinity free cycles. So maybe a more precise way to say it is if you see a 4 that is not part of this game, I mean if it's not part in the even cycles, then just contract it also, and then just do whatever you want to it because I can orient this in any way, and I still have the infinities to rescue. So you do have to be a little bit more careful in this example, but not much. Stop there. But that's good. So that means we know exactly what Coxeter systems, basically what crystallographic Coxeter groups are. They're like this. And actually, if you want to see some pictures of John of why these things are called crystallographic, she has good pictures for you.
So we got this picture here where every edge lies on a cycle.
Well, I meant to do that. I forgot. So it could be that you have
That's the degree 1 vertex. Yeah. And that, I mean, obviously here we don't care. The condition only says AP line of cycle.
And the left theorem also doesn't care, so just orient it in any way.
So you can have stuff that has no 3s and 4s as long as it has this, you know, like if you had a cycle, like all I had was infinity, 3, it doesn't matter, there's no 4s or 6.